Hi everyone, my name is Fernando, and today I will talk about semantic synthesis of specialized hash functions. So this is a work that I did with colleagues from Brazil and with David from Google. So the goal of our work is to generate code for hash functions. Um, and this code shall be specialized for the keys. We shall deal with different kinds of specializations. They will apply when you have some constraint on the key. For instance, the keys may have constant length, like 11 bytes on an American social security number. They may have constant subsequences, like the hyphens on the SSN. Or they may have some constrained byte ranges. For instance, if you look into an SSN, we see that some of the bytes, they encode digits. And in the end, we want the specialized hash to be faster. And we are willing to sacrifice distribution to achieve that goal. So by distribution, when we have a hash function, usually we want it to more or less be uniform over the image of the function. And we get that once we use functions from STL or from Abseil. Our functions, they are likely to be skewed. So, ideally, if you have an SSN, the hash of the SSN may be the number itself. So, that's not really a random distribution. But what's a hash function? So that's a function that takes an arbitrary byte sequence and then produce a value of fixed size. It's a deterministic algorithm, and usually it's used for indexing, data retrieval, encryption, except that in our case we can't use our functions for encryption. So here we have a general hash function. So this is an implementation that I took from STL. Okay, I changed it a little bit to make it easier to read, but it's pretty much this code. You see, it's general because we have general types, we have general operations that apply on those types. There's no inline assembly here, so it's not specific to any architecture. We have general loops, so we don't assume any length of key. So there's a general hash function. And then what's a specialized hash function? Well, let's assume, for instance, that the key has always 11 bytes, like an American social security number. In this case, we can replace the loop with straight line code because we already know the length of the key. So there's no need to have a loop. We can roll the loop and remove the epilogue that we have right after the loop. So that's what we get. No loop, no conditionals, more efficient memory accesses. We know the size of the largest word that we can load at once. Now let's assume that the key has some constant subparts, like the hyphens on the SSN. In this case, we don't have to load all the data. We can load only part of it because the hyphens, they will not really contribute anything to the hash. So we can remove that, we can skip that. And then instead of working with 11 bytes, we can work with 9. Now imagine that the key range is on a subset of bytes. So, we have digits. So in this case, we don't really have to work with full bytes. We can work with nibbles, sets of 4 bits. And then we only have to consider the lower 4 bits of the key. And that would eliminate 4 bits for every byte because all the digits, they would have this common prefix 00, 11. So we can process less data. Now let's assume that the architecture is Intel. Well, in this case, we can use parallel bit extraction to load all the parts of the key that matter with one single operation instead of having all those loads and ands and ors and shifts. So that's like a particular instruction that exists in Intel. And then we only load the relevant bytes. It's implemented in hardware, so it's quite fast. Anyway, so this is what we get with specialization. We can generate specialized code. So how can we use this? We have implemented these ideas into a library that we call SAPI. It's publicly available on GitHub. It has gone through an artifact evaluation, so we got the 3 stamps. And how to use it? Essentially, we pass to our script a regular expression that denotes the key, the format of the key. So it will generate like a hash function for you. Actually, it will generate a catalog of those hash functions. So there will be like simple and complex hash functions. And then you can plug this hash function right away into the STL data structures. So at this point, we can work with 4 different data structures, so we can customize the hash that we use in your data structure. If you don't want to pass a regular expression, maybe you don't know a regular expression, you can pass an example full of a file full of examples. So that's just a text file with examples of keys. So we pass that to the key builder, and then it will build a hash function for you. We use a lattice to find the right mask of bits that I have to use, but to understand that, I have to read the paper. So I invite you to read the paper. And how good are our functions? They're pretty good. So let me show some numbers. Anyways, so here I have like a number of functions that we took from previous work. So STL and FNV are functions from the standard template library that's default in C++. Then I have Abseil. Then I have city hash that you can use as well. And I have been using GPT to generate specialized hash functions. So we have a few prompts that we give to GPT. So just we can use an LLM to produce a specialized hash function. The right prompt is on the paper, so you can read it there. And then we have like 4 specializations. So we have one that we call naive. That's for keys that have like fixed length. We have off XOR. That's for functions that have fixed length and maybe some constant substring. And then we have like AES. That's also like a constant substring and fixed length, but we use a particular instruction from Intel. And have Baxt. In this case, we assume like 3 constraints. We assume like a subset of bytes as well. So anyway, and then like in this benchmark here, we shall synthesize or shall produce 10,000 keys and use them to insert or remove data from 4 data structures. So I have a number of keys here. I have 8 in total. And these are the data structures that we're using. Anyways, so here I'm showing a summary number. So this number here aggregates what we call bucket time. So that's the time to run the benchmark. That includes like the time to generate to hash, but also the time to insert or retrieve the data from the data structure. And here, just remind you that we have like these numbers here, they aggregate 10,000 times 8 times 4 results, okay? And then I have like hashing time, so that's only the time of doing hashing. In this case, you see like our functions, they're very fast. They outperform the STL functions by 4, sometimes by 50 times, like they are 50 times faster than Abseil. And let's count collisions. So these are the number of, like this number here more or less aggregates the number of elements that fall onto the same bucket. Because these data structures, they store data into buckets. You can like have lots of data into the same bucket. And if 2 like keys, they map into the same bucket, it doesn't really mean that there's a collision, but they'll be indexing the same part of the data structure. So you see that even though our distribution is not amazing, we still get more or less the same number of elements per bucket into the STL data structures. And here the number of true collisions, when 2 different keys map to the same hash. We get like 12 collisions out of 10,000 keys. Mind it that like GPT got like quite a high number of collisions, like the functions that were produced by GPT. And so, in the end, our functions, they are very fast. They are like 4 to 50 times faster than default hash functions that are available out there. Synthesis time is super fast. I didn't really show here, but that's linear on the length of the key. And our functions, they're good for indexing data. However, they're bad for cryptography. And so, yeah, that leaves us with an open question. Can we have a fast implementation that still enjoys good distribution? So, that was my presentation. Our work is publicly available, and I welcome you to read the paper. Thank you very much for your time.